So on that note, I thought it might be a good time to read a brief message of greetings from a former Premier of British Columbia, who sent a few words to this conference. Premier Bill Vander Zalm, who was the Premier between 1886 and 1991, who says, "Our Premier of some time ago, W.A.C. Bennett, had a dream to connect rail from BC to the Yukon and on to Alaska. Yet, with today's developments, this dream is quickly becoming a reality. BC Rail is a long way towards Alaska and a connection via rail to Asia and Europe, an enormous achievement and the deal of a lifetime. Changing politicians, be it here, elsewhere in Canada, or in the USA, is not the answer. We need to change this system. The legislation drafted by my government in 1989 to 1994 initiative, referenda, and recall was a great first step, though the hardcore government that followed me admits to writing the rules so as to make it impossible to be effective. In spite of the rules, we show them the will of the people can be all-powerful when we beat back the HST. I would qualify that, though, just and add one little bit in that we, as an international organization within the Rouge, do believe that it is worth impeaching a Schrader president now and again, and Barack Obama and Bush before him both qualified for that, which would definitely allow the floodgates into a real systemic change to happen. So, with that, I would get ready to transition to our final speaker for the evening, Dr. Robert Hucks, who has been a representative of the Committee for the Republic of Canada and the International Rouge Organization for decades. Dr. Hucks will be speaking on the subject of mitigating flood and drought, taking account of the sun's activity. So, Dr. Hucks, stage is yours.
I'm sorry. Okay, so is this thing on?
I don't think it's doing much.
All right. Okay, so I'm happy, having looked at this project that Hal Hooper has been talking about, the North American Water and Power Alliance in particular, to actually be in British Columbia. Maybe you could get a chance to look at what some of these places look like. But I'm not going to be talking about Nawapa so much as developing some of the work that the Rouge Science Research Team has put out over the last couple of years, particularly the work of one of the members, Benjamin Denniston, asking the questions, well, the assumptions that underlay the development of this water and power project that go back to the 1950s and 1960s. Can we still assume that the precipitation patterns that we're looking at is what was looked at then? So this is a map of areas around the world where you have what's called the global water stress indicator, which in one sense, it doesn't necessarily mean drought. It means, all the different conflicting claims on water, agriculture, industry, what have you, environmental flows, or fishing, what have you. You're going to see this map again. And this is one other thing that you can look at, something called the Dartmouth Flood Observatory, Archive of Large Flood Events. This is from 1985 to 2010. So if you keep these two maps in your mind, you see on the one hand areas where you have shortages of water, or in some cases, actual physical drought at certain times, certain locations. Other locations, or sometimes even the same locations, you have devastating flood events. In Canada, some of the most costly disasters of flooding, people in Canada are aware of, both in British Columbia and the Prairie provinces. So the question is not, considering the North American Water and Power Alliance, the question is not so much water per se, but our ability to control the water for our needs. Okay, so this graphic is also a graphic that Ben Denniston put together using a lot of his graphics here. So basically what underlies this question of whether you have water shortages, whether you have flooding, is the fact that we have the planet, most of this, a good major portion of the surface of the Earth is covered with water. You have the solar radiation coming in, evaporating water from the oceans. And then about 90% of the water that's evaporated from the oceans ends up falling as rain back into the oceans. And about 10% of the water ends up falling on the continents as precipitation, snow or rain. And then of the rain that falls on the continents, roughly something over half of the precipitation on the continents is water that's transpired from plants, and another, looks like about 10% is direct evaporation from the land surface, and then you have the water going back into the oceans again. So it's a continuous cycle. So it's not a question of, water is something that you're going to use up. It's continually being recycled. And what's driving this is this big ball of fire up in the sky called the sun. And this is an image taken by NASA. These bright spots you see on the surface of the sun is what this looks like if you look at the sun from the very short wavelength, much shorter than the visible light. You see these bright spots that if you looked at it, in the visible spectrum, they would be dark sunspots, but they're actually producing a lot more radiation, ultraviolet or X-ray. And so you see that in this case from 1996, it was about an 11-year cycle over which the activity of the sun increases. So these bright spots in the sun, the actual output of the energy output of the sun does not change dramatically, but it does become much more active. Also, the magnetic field of this sun increases in intensity. You have what's called solar wind, these plasma coming off of the surface of the sun. And this essentially creates a whole environment which the Earth and all of the other planets in the solar system are within. So this is on the bottom in blue. Actually, beginning in the 1600s, they actually had people that would count these dark spots on the surface of the sun, this number of sunspots. And what you can see if you look at the blue chart to the right, with the sunspot cycle that we just saw, and this sunspot cycle is smaller, you can see, than the previous. And then the other thing you can see is the chart in red called cosmic ray count. And what you notice is that when the number of sunspots is at a minimum, the cosmic ray output, the cosmic rays reaching the Earth, which actually come from outside of the solar system, they're produced by energetic processes within the galaxy. So when there's very low activity of the sun, no sunspots, you get more cosmic radiation reaching the Earth because the sun's magnetic field is weak. And when the sun becomes more active, a stronger magnetic field, then the sun is able to deflect some of these charged particles coming from the galaxy. And so what actually you notice is that what the cosmic rays do and the sunspots are inverses of each other. So we're going to use that fact to be able to determine what the sun was doing before people were counting sunspots. Okay, this is a bit longer time frame. The solar cycle that I showed you was solar cycle number 23, which is the one that is to the farthest right. And you can see that's a bit smaller than the one previously. And you can see that this process, what extended back to around 1600, that they were counting the sunspots in some form or another. Then you see also a wavy, smoothed out line where they essentially average the number of sunspots over the 10 or 11-year cycle, so that you're actually getting what's the underlying activity, not so much over the short term, but over the long term. And what you see is that from around 1900 up to the present, there has been an increase in activity of the sun measured by the sunspots. But if you go farther back around the period around 1800, you have what's called the Dalton minimum. So the number of sunspots, the sunspot cycle much less. If you go back even further, there was a period from around 1650 into the early 1700s where there was almost no sunspots. The sun is very quiet. And what the implications of that are, I want to just briefly say this, then you look at what the situation is now. So this is the cycle that we were looking at previously compared to the cycle that we're now in. So solar cycle number 24, which we're at essentially the solar maximum right now. And this is the weakest the sun has been in terms of solar activity since the 1800, which was the period leading into this Dalton minimum. You see that right around 1800, or a small cycle. So all the indications are that not only is this solar cycle very weak, the indications are that the next solar cycle will be even much weaker. They can look at things like the magnetic field of the sun, the various processes going on inside the sun. They can judge by processes occurring at the surface of the sun. So there are many indications that we could be looking at minimally a cooling period like the Dalton minimum, and potentially like a period in around 1600 to early 1700s called the Maunder minimum, which is much very, very weak sun. So the implications of this is a picture of the frozen River Thames in England, 1677, right in the middle of this Maunder minimum. There's a term called the Little Ice Age, which actually refers to a longer period of time. This Maunder minimum is the coldest part of this Little Ice Age, about 1650 to 1700. So we're potentially headed into something that's cool, perhaps even something like this. Period. So this is a chart basically using the fact, as I said before, if you look at the number of cosmic rays reaching the Earth from the galaxy, when the sun is very active, it has a stronger magnetic field, so that the number of cosmic rays reaching the Earth are very low. On the other hand, when the sun is very quiet, then you get an increased cosmic radiation. So this is, in a certain sense, the inverse of what we saw with the sunspot cycle. So this Maunder minimum we saw is the quiet low point where there was no sunspots. This shows up as a large increase in cosmic radiation. What that means is that it's a very quiet sun. There's possibly cooler, and because you have a large amount of cosmic radiation hitting the Earth, one of the things that has been known is that the role of cosmic radiation, which are electrically charged particles, ionizing gas within the Earth's atmosphere, and these ions that are formed in the Earth's atmosphere become the nucleation centers for forming droplets that essentially become cloud cover. So that when you have a lot of cosmic radiation, you tend to have an increase in cloud cover, which means that the planet tends to cool down, which is one of the factors, not the only factor, but one of the factors involved here. So I'm just going to show a couple of slides that Ben Deniston presented in one of the LaRouche Pack New Paradigm for Mankind shows. First, he discussed a series of studies on what the effect of weak solar activity is within 3 different areas. So first, dealing with areas that are in the northern part of the planet. Okay. Now, this is a study that was done in 2010. Are cold winters in Europe associated with low solar activity? So this is looking at this period that we saw before, the Maunder minimum, where there was essentially no sunspots, very weak sun. And we already saw this picture. This is the period where you had the frozen River Thames, the very cold period. And this is what they show here. And they look at the kind of weather patterns that are associated with that. So here's the study looking at a situation in Siberia, so the question is, how do they know how cold it was? because some of the times you're looking, it's not a question of having a thermometer in the sense that people think of a thermometer. What they did in this case is they used, in water, you have hydrogen, 2 hydrogen atoms bonded to an oxygen atom, but there is more than one kind of oxygen. Most of the oxygen in the water is called oxygen 16, so it has 16 neutrons and protons together. So that's the majority of what the oxygen is, about 99.8%. But it has a small percentage, about 0.2% of a heavier isotope called oxygen 18. And the fact that the oxygen 18 is heavier than the oxygen 16 means that if you have a warm period, the lighter isotope, the water containing the lighter oxygen, oxygen 16, will evaporate sooner than the water that has the heavier oxygen. So they can go back and look at periods where they look at the calcium minerals in living organisms and determine how much oxygen 18 is in the skeleton of some organism, and determine from that what the temperature of the water must have been. So that's what they're basically doing here. And they find that over a long period, this 1250 into 1850, which has had some cold periods, including the Maunder-Minium, some periods where it gets a little bit warmer, but the overall effect is that you have a cooling at periods where you have increased cosmic radiation. In a week's time. Okay, so the other area that they looked at is an area basically bordering the equator, plus or minus 15 degrees of latitude. And we're looking at what's the effect of having weak solar activity. This is a study that basically looked at the advance of glaciation in tropical areas where you have mountains. So you have a place in basically looks like northern Colombia. And basically you're looking at a place where in spite of the fact that it's not that far from the equator, since it's in a high elevation, you have glaciers, and over these periods, you see the Maunder minimum is one of the periods in which the glaciers advanced. So if you have an increase of ice forming in glaciers, it means on the one hand it's colder, but it also means that there has to be an increase of precipitation. So in this area, you have that increased precipitation and also cooling as a result of the weak solar activity. This is another study, basically in East Africa, Lake Malawi, and they look at basically look at determine that you have increased precipitation. Then they detail there's in terms of how the weather patterns are affected. You have this increased precipitation effect. Then this is a study in basically Indonesia, where they say on the one hand, in periods like the Little Ice Age, you have some of the lowest salinities. So it means that if you're looking at, say, a bay, or we have a river flowing into the bay, that they can measure, again, from looking at, for example, how much oxygen 18 compared to the lighter amount of oxygen 16 there is in say, diatoms or formerly living organisms. And they determined that in the Little Ice Age, you had cooler temperatures. And on the contrast, when you had a relatively warmer period, what's called the medieval warm period, from about the 9th century to the 13th century, where it was significantly warmer on the Earth than it is now, you had the opposite effect. You had, higher salinity, so less runoff in rivers. And then there's a third area that was discussed in terms of the effect of weak solar activity in this mid-latitude band. So looking at, based on studies of tree rings in Tibet, so basically what you're doing is you have a very old tree that might be 1,000 years old, and by counting the tree rings from the center of the tree outwards, they can determine year by year how much the tree grew. Is it a thick band or a thin band? And that's correlating to the temperature and to the conditions of precipitation. And they basically determined in these areas that the deepest solar minimum is this, what's called the sporer minimum. It's actually a cooler period than even the longer minimum. But that corresponded to a period of great drought from 1420 to 1570. And generally, you had problems with lack of precipitation and drought conditions during these solar periods. And then 3 areas in Asia that again looked at this longer minimum and the more larger little ice age period, where again the result being possibly drier conditions as a result of this lower solar activity. And then in the 3 additional studies in the Caribbean, where again what the result was that you have drier conditions during the little ice age or this longer minimum period. So if you look at these 3 different areas, you have this equatorial semi-tropic area that bands the equator, where you have increased precipitation. You have the mid-latitude area where there tends to be lower precipitation and a tendency towards drought. And then the northern period area where you have the weak solar activity resulting in colder winters, colder conditions. And the fact that you have around the equator, the tropical area, increased glacial advance, increased precipitation in these areas means that it's not a question of you running out of water. There's lots of water, but for some reason, in the cold periods, like the longer minimum, the ability of taking water vapor that's generated in the equatorial areas of the oceans and transmitting that into an area where you can get precipitation falling in this mid-latitude region is not functioning properly. So it's a question of transporting water vapor into these areas. And so if you return to this map that was shown earlier, just compare this to what we saw before. This mid-latitude area where there's decreased precipitation, more tendency towards drought, this maps onto this area that is not getting the moisture flow coming from the equatorial tropical area that you would get under a non-solar weak solar activity. So if you sort of think of that in terms of the current situation in North America, where you have, this is the current situation as of about a month ago in North America, the very severe drought in California, the extended drought areas in the southwestern part of the United States. And while there's certain areas in Canada that have some dry areas, you don't have the same problem in Canada. This, again, this is the North American Water and Power Alliance proposal that Hal Cooper was talking about, with the various extensions that have been contemplated, into Mexico, along the east and west coast of Mexico. 4 additions also inside the United States in terms of increasing the water flow. Mapped onto what the current idea of what the precipitation patterns are for North America. But based on what we just have seen, the question is, well, how do you know what the coming period is going to have, given the fact that the indication is that the current solar cycle that we're in is much weaker than the previous solar cycle, and there's reason to believe that the next one is going to be even weaker. So the indications we're likely going into a cooling period that could have the kind of problems that were indicated before in terms of lack of water in this mid-latitude area in particular. So that brings us back to, again, this question that there's still as much water as there was before on the Earth, and you have, say, 90% of the water that's evaporated from the oceans falls back into the oceans as rain. Now the question is, does 90% of it fall back into the oceans as rain? Does that increase or decrease when the sun becomes less active. The amount of moisture that gets evaporated in the oceans and then is in a situation where you can transport this moisture into the appropriate continents, like North America, this mid-latitude range. So the real question is not just these absolute numbers, but what's the, what are the processes that determine whether this is greater or less, and how do we put this process under control? Now, just one indication of the kind of thing we're looking at. This is a image put out by NASA's Jet Propulsion Laboratory, January 8th, 2012. And what you're looking at here, this is an image taken by the JASON-2 satellite, and what it's actually measuring is the elevation of the ocean surface, and areas of the ocean surface that are lower elevations show up as blue, and areas that are essentially a higher level, but sort of like an equilibrium level, are green. You see the chart here. And then areas that are sort of higher than the average show up as red. So this, in January 8th, 2012, this was a phenomenon that people have heard called La Nina. And basically what you have, the process, you can't see the coast of South America that clearly, but what you have is you have the western part of the Pacific. You see these red areas where it's red because the water is physically higher, partly because when the water is warm, it occupies more volume, but also because the water vapor is evaporating. You have water vapor going up into the atmosphere. You have, on the other side of on the east side of the Pacific, you have the trade winds that are blowing across the Pacific and causing the cold water underneath the surface of the Pacific to well up. So you're bringing cold water up to the surface, which is why this is cold water, and displacing the warmer water into the western side of the Pacific. And under these conditions, you have a certain process that occurs in terms of the circulation patterns. In the same kind of period, this is what was happening in terms of the moisture flows within the atmosphere. So in the western part of the Pacific, you have at a certain level in the atmosphere, the colors basically indicate the wind speed. So the red indicates that you have the moisture flow in the atmosphere moving very rapidly. Then as the colors change to green and yellow, the speed of the wind is decreasing. So you have whatever moisture that is in this Pacific jet stream going over to North America. You see that it's diverted north into Canada. Okay, and at the same time, you see that you don't have moisture flows hitting the Pacific coast of the United States. You have this high pressure area, and the consequence of that for Canada in April 2012, as a result of this kind of phenomena, the La Nina phenomena, you had very large buildup of snow in the mountains in northern United States and British Columbia. And when this snow began to melt, along with a certain rain falling on the snow, you had in the Columbia River that year of 2012, you had a larger amount of water in the Columbia River than was in the Columbia River in 1948, when you had the historic flooding of the Columbia River that people might have heard of. It was the floods in 1948 that resulted in people saying, well, we have to build the dams on the upper Columbia River. WAC Bennett ended up going ahead with. In comparison, in 1948, the flood peak was about twice as high as what you see here. So for over a month, we had this flooding conditions. And then for the United States, in this same period, in beginning of 2012, you have, as a result of this moisture flow in the atmosphere not hitting the Pacific coast of the United States, this is what you had of a general dryness in the Pacific coast of the United States. At that point, there was actually a more severe drought in Mexico. you have in basically August 19, 2014, you see what has changed now. This pattern has changed somewhat, and the question is, because basically what happens is that you have, at a certain point, you have a weakening of the trade wind blowing west across the Pacific, and the water that had been piled up in the western part of the Pacific, the red zone. See, this red area is beginning to move towards the eastern part of the Pacific. So the question is this different kind of phenomenon. It's called El Nino, where you have, instead of the cold water off the coast of South America, when El Nino is actually developed, you have a warm water, okay, and you have a certain result of that in terms of increased precipitation for the southern part of the United States and other areas. Corresponding situation in the United States, because so you have this alteration between the warm water, the cold water off the coast of South America, and the associated weather patterns. So the point being that you have how much water is being evaporated by the sun only to fall in the ocean rather than being distributed onto the continent. Nevertheless, there are periods in which you have large amounts of moisture that can be delivered in what's called atmospheric rivers. This is December 2010. You have this area which is an indication of moisture in the atmosphere. And in this particular storm, you had the effect of 17 feet of snowfall in the Sierra Nevada and 26 inches of rainfall in California as a result of this. This was just a periodic phenomena. It happens a couple of times. So the real question proposed is, what's driving these systems? What is the process that would allow us to be able to determine how these processes work? Whether you just have flooding for this, or you get the amount of moisture you need. So one approach to dealing with this situation that we're likely going into a period of increased dryness within the mid-latitudes as a result of a weaker sun is to be able to compensate for the fact that we've got a weaker sun by doing things that the sun would do for us if this wasn't a problem. There's an approach to actually increasing the ionization in the Earth's atmosphere by basically setting up. This is a company called Ionogenics, and they have this technology called EVI. So they basically set up a structure where you have electrical wires and high voltage. It's a direct current associated with this, might be like 100,000 volts. And as a result of this, you're causing the oxygen and the nitrogen in the atmosphere to be ionized, remove some electrons from them, or add electrons to the ions. And the effect of this is that you have in the Earth's atmosphere, you always have a certain amount of water vapor. But for that water vapor to condense to form droplets that can aggregate to form essentially clouds and can get rain, you need a certain condition to cause this nucleation to occur. And it's actually much more effective if you have an electric charge that will actually attract the water molecules and begin to form these droplets. So this approach is something that in several different countries has been tried. This is a study in one of the provinces of Mexico, actually several provinces in Mexico, where the chart on the top indicates the purple and the green are the low and the high estimates of how much rain that they were expecting in this year, and then the blue is how much rain actually occurred as a result of setting up these ionization stations. And so over a series of these networks, they actually cause an increase of precipitation of a substantial amount. So this is one of the things that could be done to deal with this cooling period we're going into. Okay, and this is something that I was going to mention, but just how it's already gone through this in terms of how we can also deal with this by sun is evaporating water in the ocean, and the water is being delivered to the continent by that process. Mankind can actually use, nuclear power or thermonuclear fusion, which is even better, to actually directly desalinate. This is the map that we showed earlier in terms of the ability to deal with this problem through desalination. And as he also mentioned, right now the Colorado River Basin, there's a study done recently that indicated in the Colorado River Basin, you see here, this is the Lake Mead behind the Hoover Dam, and the white areas that you see, this is where the water level used to be compared to what it is. But there was a recent study done indicating that in the Colorado River Basin, 65 cubic kilometers of water had been drawn down over a 10-year period. But most of that was not what you see here. It was not surface water. Most of that was groundwater. And so one of the things that Ben Denniston and the Drought science team have been looking at is what would be required to deal with that, because you're dealing with the ability to make up for a lot of damage that has been done over the lack of dealing with this. The ability to use helium-3, okay, to have a thermonuclear fusion base. If you can compare the amount of helium-3 that you would need to drive a fusion power plant to desalinate water and the amounts required to replenish the flow of the Colorado River. The calculations he did indicated about 1/3 of a ton of helium-3, what you could put in the back of a pickup truck, compared to if you wanted to do the same thing with a coal-fired power plant, you would be dealing with millions of tons of coal. You would take up the entire train going from the southern to the northern border of California. So the implications being the importance of these breakthroughs in thermonuclear fusion and the whole change in orientation that's going to result from this orientation as well. That's basically what